Hello everyone. In this video, we're going to be integrating a rational function in two different ways. How cool is that? We have x squared plus 1 divided by x to the fourth plus 1 dx. Of course, we're going to integrate with respect to x. And let's see how we can do this in two different methods. Okay? Let's start with the first one. Bear with me because this is probably going to be a long video. Now, we're going to start with the following, which is called partial fractions. Partial fractions is basically like when you add two fractions to, you make a common denominator, so on and so forth, and at the end you simplify it and you get a simplified expression. How about reversing that process, right? Kind of like reverse engineering a rational expression to kind of break it down into pieces so that it's easy to integrate. That's what we're going to do. First of all, I want you to notice that x to the fourth plus 1 is factorable. How is that possible? It's the sum of two fourth powers. Exactly for that reason, it's factorable. And to keep a long story short, I'm just going to give you the factors, and you can definitely check this out because I went over these in my videos many times. X to the fourth plus 1 can be factored into x squared plus root 2x plus 1 multiplied by x squared minus root 2x plus 1. Just try to explore, think about it, how you can factor it this way. It's going to teach you a lot. Okay? Now, once you have the factoring, we can go ahead and try to break this down. Since we have two quadratic factors, our denominators are going to be quadratic and they're not factorable, nicely. So our numerators will have to be linear, okay? There's a good reason behind that. So we're going to assume something like ax plus b divided by x squared plus root 2x plus 1 plus cx plus d, another linear term, for the other factor, which is x squared minus root 2x plus 1. Great. Once we achieve this, like find a, b, c, d, we're going to have two integrals that are obviously a lot easier than the original one. So by symmetry, we can kind of use c to be the opposite of a and d to be equal to b. So we can kind of get something like this. So that kind of simplifies the process, and that actually works from symmetry. And again, think about why that would work, but we can basically assume that our integral is going to look like this, okay? All right, now, after writing it that way, we can solve for a and b, and how we do that is make a common denominator, but of course, you're going to have to take this, multiply by that, take this, and multiply by that, and it's going to create a gigantic messy term. You kind of have to simplify it, or you can do this after multiplying things. You don't have to distribute, replace x with certain values like 0, 1, -1, stuff like that. At the end, you're going to find the a and b values. To keep a long story short again, I'm going to give you that a is going to be -1 over 2 root 2, and b is going to be 1/2. And of course, this works for c and d as well. Okay. Great. Now, our integral is going to turn into something like this. We're going to have negative x divided by 2 root 2 plus 1/2, of course, because of b, right? And all of that is divided by x squared plus root 2x plus 1. And of course, there's a dx at the end, right? Don't forget that. And our other integral, which we separated, x divided by 2 root 2. Let's clean that up a little bit. And then plus 1/2. And the denominator is going to be the other one, x squared minus root 2x plus 1. And of course, we still have the dx. Okay? Now, what do you do with this? Well, we kind of need to work with the denominators, right? We want to complete the square on this one. So let's go ahead and take x squared plus root 2x plus 1 and write it as x plus root 2 over 2 squared, because you kind of have to take the half of that. And of course, that's going to give you a term which is 1/2 as a constant, but you need a 1, so you need to add another 1/2. Make sense? And for the other one, something similar you need to do. Once you do 1, the rest is easy. It's going to be the same thing, but this time it'll be the -1. Of course, you have to add 1/2 at the end. Okay? So far, so good? Great. Now, what do you do with this? Well, you place it in, and of course, this kind of gives you an expression where you can kind of go with the u substitution and integrate, okay? So that should, from there, you're going to get an expression that is basically easy to integrate, but you kind of need to go through the work. Okay, so what does this result simplify to? Let's go ahead and write it down. Again, without further ado, I'm going to show you or give you the end solution, because this is really going to take a long time and I don't really have time for that. Okay, too bad, right? So the solution of this integral is going to look like this. We're going to get 1 over 4 root 2 as a constant at the end. We're going to have ln, and if you want to use the absolute value, that's fine, but I usually skip it. X squared minus root 2x plus 1 divided by x squared plus root 2x plus 1. That's going to be the first piece, and of course, then we're going to have the other piece, which is 1 over 2 root 2, and we're going to have some arctangent here of root 2x plus 1. Actually, I kind of need to make more room for this, so let's go ahead and move this to the left a little bit so that we can fit it there. Great. And then the other expression is just going to be another arctangent plus arctangent. Oops, let's erase this and make a little bit more room. Plus arctangent square root of 2x minus 1. And at the end, we're going to add the constant. Now, why did that happen? Because when you did this, you kind of had to split it up. You're definitely going to get like a 1/2 from here and other constants as well. But this is an arctangent type. Let me tell you why. Because if you call this u and you call this a squared, you're going to get something like u squared plus a squared in the denominator. And that's exactly arctangent. And how to find out is that you can replace u with something like a times tangent theta. And if you find du, it's just going to be the secant squared, so on and so forth. And you can write in terms of a, and then so much work, it'll give you this at the end. But to keep a long story short, I just gave you the solution, okay? So this is basically the first method. Go ahead and give it a try and see if you can find the exact same solution. Now, here's the second method, obviously, which is much, much cleaner in my opinion. But again, you get to decide. So again, we have x to the fourth plus 1 divided by x squared plus 1. Is that the original integral? Or it's the other way around? Actually, it's the other way around. It can't be like that. Otherwise, we couldn't do the partial fractions. Like we would have to do division. Okay, this is our integral. And the cleaner method is basically noticing that x to the fourth plus 1 can actually be factored into the following. We'll take out an x squared. That's going to give us an x squared here. Nice. But then, to get 1, we do need 1 over x squared, right? Okay, so what is that supposed to mean? Well, here's the thing. We're going to go ahead and use a special substitution because of this numerator, okay? This numerator tells us to use something like this. And again, this may not be obvious right away, but this will work. U equals x minus 1 over x. Now, the reason behind that is the derivative of 1 over x is negative 1 over x squared. So when you pick something like this, you're going to get that when you differentiate. Does that make sense? I hope it does. When you differentiate this, you're going to get x squared plus 1 over x squared with a dx, of course. And now this will work very nicely. And of course, you can kind of, if you want to, oops, I messed up. The derivative of x is 1, so it's going to give you 1 plus 1 over x squared, not x squared plus 1 over x squared. So I was wrong when I said it's going to give you this when you differentiate. That was wrong. Okay, it's going to give you 1 plus that, but this is what's going to help us. Because when you make a common denominator, you're going to get x squared plus 1 over x squared dx. Beautiful. Now, since we know what u is, that's how we named it, let's go ahead and evaluate u squared from there. This is where miracles happen. When you square this difference, you get x squared plus 1 over x squared minus 2. And from here we can isolate x squared plus 1 over x squared, which is going to be u squared plus 2. Awesome. Now, we pretty much have everything we need. Now, let's go ahead and continue with our integral. We're going to go ahead and rewrite it. So now we have x squared plus 1 divided by x to the fourth plus 1 dx. It's too long. Okay, keep it short. And then now we can do the following. We can go ahead and divide a numerator and the denominator by x squared. That's going to give us x squared plus 1 divided by x squared. And as you know, in the denominator, we get x squared plus 1 over x squared dx. Beautiful. Now take a look at this. This is u squared plus 2, isn't it? And this is du. Awesome, right? Where did that come from? Remember when we called u equals x minus 1 over x, We differentiated, made a common denominator, and that's what we're getting from here. And this is super clean, don't you think? Now we get du divided by u squared plus 2, which is actually a fairly easy integral. Again, for the same reason, you can call this u equals square root of 2 times tangent theta. And from here, tangent theta becomes u over root 2. And then theta becomes arctangent u over root 2. You can kind of differentiate this. You'll get the secant squared, which is 1 plus tangent squared, so on and so forth. And at the end, you're going to get something like this. Ready? 1 over root 2 multiplied by arctangent u over root 2. You can also memorize this as a formula. I think this will be helpful if you have du over u squared plus a squared. It's just going to be 1 over a times arctangent u over a plus c. Okay? That will be super duper helpful in these scenarios. Great. So that's our integral. So as a result, we have the solution x squared plus 1 divided by x to the 4th plus 1 dx is equal to 1 over root 2 multiplied by arctangent, and then x minus 1 over x divided by root 2, and at the end, of course, do not forget the plus c. Obviously, this is a much faster method, but the key is to be able to recognize that u equals x minus 1 over x is going to be helpful in these scenarios. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. By the way, compare this to the first method and see if they do agree in a way. And until next time, bye-bye.